Welcome to our next video for Stat 212. In this video, we're going to talk about odds ratios. And I'll give you a heads up, odds ratios are a little confusing. In this class, we're not really concerned with calculating them by hand, though I think you should know how to do them by hand, as much as we're just kind of focused on why we use them and how you're going to see them if you read, say, a journal article and kind of the context that they get used instead of, say, relative risk in certain cases. So first off, we're going to start with calculating odds and just what it is. So odds is just another measure of comparison between two groups. It is commonly used in medical studies, as we'll talk about in just a second and why. So first, let's just compare odds versus risk, or just normal probability, I guess. So if I asked you, what is the probability of rolling a 6 with a 6-sided die, how would we calculate that? So hopefully you remember from chapter whatever it was when we did probability, that this is just going to be 1 out of 6. In other words, it's going to be number of ways to get this result divided by number of total possibilities. In this case, since they're all equally likely, I don't have to weight anything or think about it more complicated than that. I just know that if I have equally likely possibilities, equally likely outcomes, it's just the number of ways I could get this divided by the total number of ways possible. So that would be a probability. We could also think of risk, as we've calculated so far, like absolute risk, as being the same thing. It's just the number of people who get something out of the total. So we talked about the risk for, let's see, let me think of something easy. Like the risk of COVID, for example, given that you are in a particular community. We might say that if 100 people out of 5,000 have COVID in this community, the risk of COVID, or the likelihood that you have COVID, or the risk of having COVID is 2% right now. So that would just be a very simplistic example where a risk is really just kind of a probability, the number of people with divided by the total number of people in that community. Now, the odds are going to be a little bit different because odds typically are like a comparison directly of two values, of two groups, rather than something out of a total. So if we were to say, what are the odds of rolling a 6 with a 6-sided die, we would say that the odds are 1 to 5. So 1 to 5, usually we write it like with a colon notation. We could also write it as a fraction and say the odds are 1/5. And what we're trying to say is, again, like we're comparing two things. We're comparing the likelihood of having it, so number of ways. Let me write this more consistently. So number of ways to get this result divided by number of ways to not get this result. So you can see this is a little bit different than just risk or simple probability. So now it's a direct comparison of two groups and how many we have in each group and putting them together into some kind of value. So the odds are 1/5, are 0.2, whereas the risk or probability up here is 1/6 or 0.167. So before we talked about kind of the estimated relative risk for polio with the Salk vaccine. So again, we say estimated because it's technically a sample. So we're estimating what that true parameter is. And our estimate for the relative risk was 0.28765. So we're taking the number of people with polio divided by the total number who got vaccinated over the total number of people with polio divided by the total number of people with just the placebo result to compare these risks. So this is the absolute risk for polio with the vaccine, the absolute risk for polio with the placebo shot. So we can compare those in a ratio and call it the relative risk, or sometimes called the risk ratio. However, we could also do something called an odds ratio, and that's if we take the odds of polio, or the odds of the agent of concern, or not agent, the outcome of concern. So the odds of having this outcome of concern for this group divided by the odds of having that outcome of concern for that group, and calling it an odds ratio. And you'll notice the difference here is what we're dividing by. We're not dividing by the total, we're dividing by the number without polio from this group, the number without polio from this group. And that's why you see that small discrepancy in these numbers, is we're just taking the 33 out of here and we're taking the 115 out of here to get those numbers. So if you look back at this table way back here, we're doing 33 divided by this number, 115 divided by this number for odds. It's 33 divided by this number, 115 divided by this number for relative risk. So if I go back somewhere, oops, that's too far. There we go. One thing you'll notice, though, is that if we calculate the odds ratio using these odds instead of risk, my outcome is almost exactly identical, right? So 0.28753 versus 0.28765. These are almost identical. So why are we doing this if we're getting basically the same number? There's two things to note here. Number one, if we're starting with a really, really large sample, odds ratio and relative risk are basically the same measure. The difference is going to be super negligible in these cases because the difference between adding in these numbers and dividing is going to almost cancel out the difference at that point. It's going to be so minuscule a difference. So whenever we have a really large sample, odds ratios are really approximating relative risk. However, if we have a smaller sample, like a couple hundred, we're going to notice we're going to have a more noticeable discrepancy between those two values. And the other thing to keep in mind is that an odds ratio will always exaggerate the effect in comparison to relative risk. So in other words, relative risk is always going to be a little bit closer to 1 than the equivalent odds ratio calculation will be. An odds ratio is going to be a little bit closer to 0 or a little bit closer to positive infinity, depending on which way the direction seems to be going there. So odds ratio is always a slightly exaggerated relative risk measure that will be closer and closer and closer to approximating relative risk when we have a large sample. So in interpreting an odds ratio, we're going to do kind of the same thing here, except that instead of saying kind of the estimated risk, we're going to say the estimated odds of getting polio after taking the Salk vaccine as compared to taking the placebo are 0.288 to 1. Again, I'm just rounding there, 0.28753 to 1. So notice that the framing is just that I'm using the word odds, and more commonly with odds, we might use this word of some number to some number, something to 1. Whereas in relative risk, we might say it's this number times the risk of the other. Okay. Also, something that I'll notice here is that we talked about which number goes in the numerator, which number goes in the denominator. It doesn't really matter that much as long as you're being consistent and you're interpreting appropriately. So if I want to flip this around, I could say that the estimated odds of avoiding polio, the estimated odds of not getting polio with the Salk vaccine as compared to taking the placebo are 3.4779 to 1. So I can use that language and switch it around if I want to just take the reciprocal of this value. Now, something that I'll also notice here is that this 3.4779 is above 1. And so a lot of times you're going to read journal articles that will always report their odds ratios, or relative risk for that matter, as values above 1. And they always write the interpretation in favor of that apparent group. So just keep in mind that that's a common practice when you read an article, is to report ratios as being greater than 1 and writing the direction to kind of match whatever it is to make those numbers greater than 1. Okay, so when would we use an odds ratio? So we talked about how it works and how it compares to relative risk, but we haven't really explained why we need this value at all. So the answer here is that it depends on the study context, because there's going to be some situations where we can't accurately estimate the relative risk value, but we can calculate an odds ratio and know that it should be approximating the relative risk value. So we're going to kind of look at a situation here. We're actually going to look at two different study contexts with two different sets of data. We're going to calculate the relative risk values make some observations, and then calculate the odds ratio values and make some observations and see why the study context matters and how this affects things. So on the study on the left, this represents a cohort study with 200 women who had this potential risk factor gene for ovarian cancer, and 200 women who did not have this potential risk factor gene for ovarian cancer. And so since we're doing a cohort study, we are identifying these participants based on whether or not they have kind of this treatment factor, this risk factor, whatever we want to call it. And then we're going to see what happens. We're going to see if there's a difference in this outcome of interest between the two groups. So in the case of the study where women had the gene, we noticed that 15 of them eventually developed ovarian cancer out of 200, whereas in the no gene group, only 1 out of 200 developed ovarian cancer. Now let's compare this to a different study context on the right, where the data on the right is a case control study, where the researchers identified 200 patients who already had ovarian cancer and 200 who did not. And then examination was done to see which of these women apparently had this possible risk factor gene. And we noticed that of the 200 women with ovarian cancer, 172 had the gene, 28 did not. Of the no ovarian cancer group, 46 had the gene, 154 did not. So, in these two different study contexts, if we're trying to analyze what's going on and compare and make a statement about whether there's a link between this gene and ovarian cancer, we have to think about the way that data was collected, and this is going to get into the measure that we use. So let's start by calculating a relative risk value for both groups and looking at what happens. So I'm going to be lazy, and I'm going to use a calculator for this because I'd like to also get the confidence intervals for these relative risk estimates, because those are going to be really telling here as well. And I have to, having a little bit of trouble opening this calculator. I think what I can do though is I can go to here and I can just cheat. So let me do that. So I'm going to go to this relative risk calculator, and I'm going to change these numbers to 15 and 1, and I'm going to do 185 and 199. I'm going to do 95% confidence interval. And so what you'll notice here is that I have 15 women exposed to the gene who got ovarian cancer, 1 exposed to the gene who did not. One not exposed to the gene who also got cancer, and then the rest are in the no cancer group, some of which are exposed, some of which are not. And so my estimate for the relative risk is going to be down here in the next table. It's going to be 15. And notice my confidence interval, though. My confidence interval is going from a relative risk estimate of 2 to 112.48. That's an enormous difference there. So my relative risk value here, my estimate, I'm going to put a hat on it because it's an estimate here, is 15. And my confidence interval is going to be 2.00 to 112 point something something. I forget what that number is now. I want to say it's like 48. I hope that's 48. I don't know. That's an enormous confidence interval. So let's just kind of make a note of that. Enormous interval. So even though I have my RR hat of 15, I'm not very confident in that value. It could be off by quite some magnitude. I'm pretty confident that it is above 1, since my interval is starting at 2. But beyond that, I have no idea what's going on. Now let's do the same thing for the example on the right. This data is collected very differently though. And as we're going to see, a relative risk estimate doesn't quite work in this context. But again, now I can open it, I think. Or can I open it? Do I have to? There we go. That's helpful. Okay. So I'm going to do, let's see, I think it is 172 and 28. And then this group is going to be 46 and 154. And this is, again, going to be 95% confidence. Now my relative risk confidence interval has a point estimate of 5.13. and it's spanning from 3.62 to 7.26. So it's going to be 5.13, and my interval is 3.62 to, what is it, 7.26, I believe. So that interval is a whole lot better. However, this relative risk calculation is problematic, and that's because I am assuming that this is natural incidence of ovarian cancer when it is not in this particular group. So in other words, if I think about how my relative risk calculation is being calculated, it's going to be this 172 divided by 218 over 28 divided by 182. And you're going to notice the risk of ovarian cancer is not 172 over 218 if you have the gene, and it is not 28 over 182 if you don't have the gene. Those numbers are both way overestimates of the natural incidence, and that's because I did a case control study where I sampled from the outcome equally rather than probing natural incidence and just getting people from each subgroup and seeing their natural incidence of ovarian cancer over time. So this is problematic. So I'm going to put a big red X, and I'm going to say this is a bad calculation because that measure is now meaningless if I don't have natural incidence sampling to accurately measure those things. And by dividing it, I'm not taking it back. I'm not fixing it. I'm just dividing two numbers that don't work, and I'm dividing them in such a way that my outcome is nonsensical. Or nonsensical. Nonsensical, I think is the word. Okay. So on the left, the issue here is that we don't have enough data. To accurately estimate RR. So even though we can come up with a point estimate, we can produce an interval, our interval is so enormous that it's not super helpful. And that's the case when we had this low incidence kind of situation, that it's kind of hard to find people who get ovarian cancer unless we have a really large sample of people that we're beginning with. Obviously, that's a possibility. There's some studies that do that. But if we can't do that because of resources or whatever, then it's just going to be really hard to get a good estimate of the true risk for ovarian cancer in each of these groups, especially the no gene group for comparison. Now, the issue on the right is that without, I'm going to call this natural incidence sampling, and I know I'm not defining this word anywhere else, but the idea is if I'm sampling from the outcome, if I'm doing a case control study, then I don't have the natural incidence of ovarian cancer. And when I don't have that, I can't trust my RR calculation. All right. So now we could do the same thing, instead calculate odds ratios for each of these data situations. And so I'll go ahead and open this up. So for the odds ratio for the group on the left, again, I'm going to have the same inputs here. Oops. Okay. Come on. No. Okay. There we go. 185, and oops. This is doing this right. Okay, yeah, 199. 0.95. And now this is an odds ratio calculator that I pulled up. So now my values are going to be, my OR estimate is 16.14. My interval is going to be 2.11 to 123, something like that. So 16.14. Come on, there we go. So OR hat, I should go back to black. I think it was 16.14. Again, my interval, goodness, I've already forgotten what it is. It's really huge, right? So it's like 2 point something to 123 something. So that's kind of the bottom line here is my interval is still enormous. So this is kind of a problem for the same reason that my relative risk interval is too big. So that's why these are kind of poor estimates. This is also a poor estimate because it's just the interval is too big. However, if I calculate an odds ratio over here on the right for this case control study, my values are going to come out a little bit differently. So my odds ratio, I'm actually going to calculate the odds ratio right here. The odds ratio is going to be 172 over 46 in the numerator, and it's going to be 28 over 154 in the denominator. And if I calculate these numbers out, I'm going to get 172 divided by 46 divided by 28 over 154. I'm going to get 20.56, 20.57, something like that. And you might be thinking, well, hey, like, isn't this a problem for the same reason that the relative risk measure doesn't work, because we don't have natural incidence sampling? And the answer is it's complicated, but it works. Mathematically, even though these numerator and the denominator themselves are not accurate measures of the true odds of ovarian cancer for each group. So the numerator is a problematic measure of the odds. The denominator is a problematic measure of the odds for the other group. But when you take when you divide one against the other, that bias or that problem actually goes away, because the amount of inflation in the odds measures are equally, or they're both inflated by the same amount, such that when I divide one from the other, it actually fixes itself. Now, we're not really going to break down mathematically why that is. If you want to, you can think about it for a good 30 minutes, and maybe it will make sense. But I'm not going to worry about it because I don't really care if everyone else understands it here. But the bottom line is that this works, and that fixed the problem that the relative risk measure will still have. And so my interval, I didn't calculate it. You can, if you want to open the calculator, you can do that. But my confidence interval is also going to be kind of similarly narrow, much like the one that's above. At least it's narrow enough in comparison to the ones on the left. And this kind of works as a reasonable measure of that comparison. So believe it or not, this one will actually work. So dividing one odds value from the other actually adjusts the bias, or you could also call it the inflation, and accurately reflects the true odds ratio. And something else that I'll kind of point to here, notice that this value, 20.57, is actually reasonably close to the 16.14 I have on the left. Now, that measure is prone to a lot of error because the interval is so huge, as we've seen, but you'll notice that it's still kind of in the neighborhood, reflecting that it's still measuring, like, even though I have a different data context, it's still measuring a very similar thing. Whereas up here on the top, my relative risk measure on the right is quite far away, and it's not in that ballpark really compared to the 15 that we saw on the left. And so that's because, again, if you remember the fact that the farther I get away from one, the crazier the scale gets, right? So like, 10 is equivalent to 0.1, 5 is equivalent to 0.2, 2 is equivalent to 0.5 in terms of being on either side of 1. So being farther and farther ahead is not quite as like crazy as you might think of it as. So 16 is actually relatively close to 20, if you want to think of it that way. Whereas 5 is actually kind of some distance from 15 if you think about it as being kind of 3 magnitudes away from 15, whereas 16 and 20 are relatively close in magnitude in that sense. So again, the point here is when I'm measuring something that's kind of low incidence, I'm typically going to choose the case control study over the cohort study because it's really hard to get enough data in a cohort study to accurately measure this risk of a low incidence thing. So rather, I'm going to go straight to the source, and I'm going to get people who have the condition, who have this outcome of interest versus those who don't, and then see if they might have had the risk factor. And so when I do that, I can get much better estimates. I have more relevant data to use to make these predictions, but I lose natural incidence sampling. Relative risk will no longer work, but I can use an odds ratio, and an odds ratio is an approximate measure of relative risk and is useful in these kinds of comparisons. So if you understand this general notion of why we're doing it, even if you don't understand mathematically what the difference is, that's okay, as long as you understand the reasoning of this is a thing that we use and we use it in the context of a case control study.